Hey, this is Chris. I'm going to share a little bit about a project that I started a while ago when I started getting interested in the ZX Spectrum Next. Really just started out as a toy project, trying to see what it would take to generate code for a Z80 CPU, and evolved from there into an almost fully fledged language. Right, so let's get started. The compiler itself is written in C#. Over here what you're seeing is a small little program written in the ZXN language. Prints a line, ZXN compiler, and then another line for the ZX Spectrum Next. And on the right hand side in CSpec you can see the result, and below that here in VS Code you actually see the assembly code that was generated for that little program. Right, so let's stop that program. Let's look at what we can do with the compiler. Right, first of all, let's look at some variable declarations. Var I equals 10 declares a variable called I with the initial value of 10, and that will be inferred as a int 16, right, which is a signed value, and we can compile that quickly. You see when I compile it, the code that's generated is really just this single line, generating a global variable underscore I, right, corresponds to the original name, just prefixed with an underscore, defined as a word, double byte, right, and the initial value 10. I can also create a uint j, can be initialized, right, and compile that. We'll see, we get a new value there, or I can have it uninitialized. I want to compile that, be declared as a 0. As a free line, I can say j is equal to 54 and compile that. You see the code that gets generated, the two declarations, the memory reserved for the variables, and does the actual code that does the initialization. HL is loaded with the value 54, and then that value loaded into the memory location pointed to by j, or underscore j. All right, so really straightforward. There's basics of variables, number of data types supported, including strings, arrays. You can even create structs in the language. We'll see some more of that later. All right. Obviously, as you saw earlier, there's simple statements like print line. All right. And we can compile that. All right. There, a global literal string was created. Hello, it's length prefixed. Also, null terminate these makes it easier when we're dealing with some of the ZX Spectrum Next APIs that expect null terminated strings. So we've got length prefixed as well as null termination mixed in there. And then the actual code that executes, we load the pointer to that string into HL, call a library function that we have as part of the compiler called euler.printString. And then we load A with 13, which is the new line, since we used print ln, and output that character to the screen, which will put a new line. Right, so let's run this. If in Visual Studio Code, I just execute this code, we'll assemble it with the awesome SJSM Plus, and start running. And when I execute, there we see our hello. And we'll also do other control statements like for loops. I equals 0. Right, initializing the control variable with 0. Continue to loop as long as that control variable is less than 10, and we want to increment the control variable by 1 every time. Right, and what do we want to do? Let's print ln open brackets the value I, and the word line. Let's go for that. Then we end our code block. Push F5 to compile that. You'll see that all of our code is generated here, a little bit more complex, but nothing too crazy. Right, that's the loop. You'll see all these ZXN DBG line comments. They're actually special comments that allow me to do source level debugging with another great tool called Dzog, which is a debugger for typically for assembly code, but I've managed to get that to work with this language as well, so you can actually step through the code you see in the text editor here and watch it execute. I'll show some of that in a later video. Right, let's run this code now. So we'll stop the current execution. next to you, and there you see each one of those lines got printed out as expected for the code that we have. Other constructs that we have, if statements. You can say if some condition a is less than 10, print ln 10, else print ln and we're in that block. So if supports else if as well, blocks. So you can put in your code there, if statements. In addition to that, we have while loops. We've already seen the for loop in the previous example. Yeah, I can say while I is less than something, do some work, right? Increment I or increment it by 5, and that loop will loop until I is less than 10. So all the typical constructs that you'd expect to see. Let's take a look and see if we can get a slightly more elaborate example going for you here. So let's show you and I'll just copy this code from some samples I prepared here. Here we're declaring a string variable. It's uninitialized, doesn't have a value. We're going to loop the control variable from 0 to 3. Right? And then we've got a switch statement, another control structure in the language. And so whenever the value is 0 or 2, we're going to set S to even. And when it's 1 or 3, S will be odd. And then we'll print out the value I is and whatever S was set to. Let's try that out and see how it goes. We compile the code. So we'll see our code got compiled to assembly. And let's run it. And we see expected result. The switch statement also includes defaults. So what would happen if we didn't match anything? So let's, for example, just an example, I know 0 is considered even, sorry, but let's say the S is equal to some question marks. Right. Haven't got all that right, I hope so. Compile it, and we'll stop the current execution, and let's run it. And there we see 0 is, I don't know what it is because we didn't match any of our case statements. 1, 2, and 3 have the expected values associated with them. Right. So what's the purpose of creating a language? There's so many languages already. Obviously, there's a lot of us that prefer to work in Z80 assembly directly. And I say us because I've become quite fond of it over the course of this project myself. And then there's others that really enjoy working with C compiler. Z88DK is an example that I haven't used it much myself, but I think it's really capable and there's some good libraries for it. But like I said earlier, this project's a little bit of fun and also allows me to experiment. I can go and build features into the language that directly support the next. Right? And that's really what I want to get to. So I want to give you a small example quickly of just a program using the sprite capabilities. So let's have a look at this. And we'll just open this up a little bit so you can see it more clearly. Let me zoom in. Maybe not that much. Right, so yeah, I've got a byte array. Right. Again, I've said it's a byte array, but I didn't give a size. It will infer the size based on the data that's put in. And I've actually got two 16 by 16 blocks here, right, representing two separate sprites. Also, I've got libraries that I've created that provide a lot of the functionality, but I wanted to show you that you can use NextReg and set them directly. So I've said, hey, the transparency color is set to 0, because I've used zeros when I defined the sprites up here, just to keep the alignment nice and simple. And then you can use the reg 15, hex 15, to reverse the priority, so that we've got the sprites on top of layer 2, which is on top of the Euler screen, right? And we're also enabling sprites. Then here's one example of a standard function in the language called upload sprite. And I'm saying I want to load the sprite starting at slot 0. There are 2 sprites, and the data for that sprite is image, which is the array that I defined earlier. Right? Once we've done that, all the sprite image data has been uploaded to the FPGA. Now I can actually go and create a sprite instance. Right? In this case, I'm saying create a sprite in slot 0 using pattern 0. So that will be this first pattern here, which is the ball. If you look carefully, you can see it there in the 3s, right? And then it gives me back a reference to that sprite. I can now say show sprite, which will put the sprite on the screen. I can move the sprite to a location on the screen, and I can even change the pattern. You'll see that the second pattern, it's a little flag-like pattern that's spaced in the middle of the sprite. And we'll go into a little example here where we'll actually loop continuously, right? With this variable, and then have an inner loop, which we have a control variable I, which goes from 0 to 3, right? This loop here is just for slowing things down a little bit, otherwise it's way too fast. And I actually have library functions for this too. I just want to show more of the capabilities here, and we'll look at the other functions as we get to it. Right. Yeah, I decided, oh, I want to synchronize with the frame, so I actually emit assembly here. I just wanted to emit the halt statement, the halt opcode rather, so that we can synchronize with the frame rate, and then I'm calling rotate sprite, where I specify the sprite I want to rotate and which angle I want to rotate it. Now rotate sprite's a little cool. It actually uses the horizontal and vertical flip capability of the sprite, but does it in order so that the sprite looks like it's actually rotating rather than just being flipped and having the incorrect mirror image. So it sort of creates the right permutations of horizontal and vertical flips based on the rotation that you request. And the rotation is clockwise, starting from north effectively being 0, east 1, south 2, west 3. Right, so if we spin this quickly, you'll see, keeping in mind that I changed the sprite pattern from when I created it with sprite pattern 0, I switched to sprite pattern 1. So that's what you're going to see on the screen. And if all goes well, this will compile. Can flip back to the VS Code and stop what's running there, and spin up compiler. And we see our little flag rotating, as you'd expect. Okay. Right, let's look at another example. Right. Let's go look at creating functions. Right, everything I've done so far has sort of been free code at the top level of the file. We can also create a function. In this case, we created a function called fact, right, for factorial. Takes an integer argument in and returns an int. Right, and it's your normal recursive factorial implementation. Right, we'll run that. And you'll see the sprite's still on the screen when I execute this. We haven't cleared that, but we get the right answer. Factorial of 5 is 120. In addition to the integer data types, we also have floating point data types. And let me show you another example. Yeah, that's pretty fun, I guess. Right. Let's run it first. It's a little bit longer. We'll go through it. This is just again using the Euler, right? And you can see it's moving a little @ symbol around the screen, but a little bit too fast, right? So let's try and see if we can slow that down and make it more visible. Right? Let's go through the code quickly. Sets up a few variables, gets the current XY locations, but starts out in the middle of the screen. We remember the old XY. I just initialize it to one position off from the original. and then we've got a delta xy, and I made those a signed byte because I want to actually support negative numbers here, right? Because I'm going to go delta x is going to be 1 to move to the right and minus 1 to move to the left, and similarly with delta y, 1 to move down, minus 1 will cause it to move up. And I explicitly set the CPU speed to 3.5 megahertz here, and you could see the compiled code was moving that symbol around pretty quickly. Right? First line, position the cursor at the old xy and plot a space or print a space. Right? Go to the new xy, print the little symbol we want to move around, and then store the current xy into old xy. Update xy with delta x and delta y. Now you'll see I've got a cast in here because ints signed and unsigned, when you manipulate them in an expression, you can lose data. The compiler expects you to be very explicit whenever you're going to do anything that potentially loses data, right? You need to be explicit about it. So in this case, I know that I have to work with two unsigned values because x is unsigned. So I just cast that dx to an unsigned value. Fortunately, the mathematics works out just fine when you're working with bytes on a computer, so it all works out well. And then we do a test. If x is less than 1, in other words, if we've moved to column 0, then the next round we want to actually start moving in the other direction to the right. So we'll flip the delta x to the inverse of whatever it was. And also if I've reached more than 30, so we've got to 31, that's the last column on the right, we also want to flip delta x, right? And the same for delta y. So let's see if we can slow this down a little bit, and we'll use the same trick we saw earlier. Right, and we'll just put a halt in there, so at least we're synchronized with the frame rate. That'll knock it down to about 50 times per second, the updates. Right, we've compiled that, compiled successfully. And let's give it a spin. There we go. So you can see this generates fairly quick code. Right? The compiler is not awesome at optimizations, but it's got a few in. I still need to do things like more fancy peephole optimizers, but it'll do some common things. Let me give you an example. The while loop, for example. If I say while true, print ln, and I'm not going to run this because it will run forever. Okay, and let's go look at this code view here. Make sure we're at the top. Let's compile that. Right, and you'll see that the only code that actually got generated was this. Right, there's a loop label, loads the pointer to the string that we want to print, calls print string, again prints a new line, and then it loops. Clearly lacking any kind of condition. I had a while condition here while it's true, but there's no condition code generated here. And the reason for that is because at compile time, compiler saw that, oh, this is a constant that will be always true, can't change its value, so it eliminated the while and just did a straight loop, or eliminated the test for the condition. Now you can contrast that if I add a control variable here, while I less than 10, and let's go increment I, right, so if we run it, and let's compile that, and now you see a different story. We've got our loop label again. Right? HL gets loaded with the contents of I, right? And when I was generated, because it was initialized with 0, it actually initialized it in place, so there's no code generated for that initialization for global variables. Got the value in HL. We load the constant 10, which is what we're testing against, into DE. Then we call another little library function that we have to do a signed comparison, a 16-bit comparison for less than. Right? And the result of that is in the A variable. It's a Boolean result. A will be either 1 or 0, depending on that outcome. We test it for 0, and if it's 0, so it was evaluated to false, it was not less than, then we'll jump to the end of the loop, which takes us outside of the loop. Otherwise, we run in the code that we saw previously, the body. Here we increment the value of I, So we load the value of I, increment h up, and then store it back to I, and it loops back again. Right? Tests the condition, right, and runs the code. Let's give that a spin quickly. And there we see hello printed out, hopefully 10 times. Okay. One more thing I'd like to show is the use of some graphics. For that, I'll introduce a library. So we'll include euler.zxn, right? So that's a library, some library code I've written that gives us access to the graphics capabilities, standard spectrum graphics for the Euler, right? And one of the functions we have there is draw line. We can draw a line from 0, 0 to, let's go 100, 100. Okay. Underscore. Right, that compiled. Let's see the code that got generated. So here we see our values pushed onto the stack, call to draw line. Let's clear that. And there we see we have a line drawn on the screen. Also have other functions, draw circle. Right, the language is not case sensitive, so doesn't matter what case you use for variables, functions. I'll always match them as long as the spelling is correct. Right, that's the center point of the circle and the radius of the circle. Let's compile that. And execute it, and you can see the circle draws pretty quick, a little bit faster than what the circle is drawn on when drawn with basic. Right. So let's do a classic example here. Let's call it R because it's our radius, right? Less than 18. Right. Is not declared. Let's try that again. Okay. You can see exactly what you'd expect. Now let's try different speeds here. So next rate 7 at 3.5 megahertz. That's 0. That's what we just saw. And let's push that all the way up to 28 megahertz. A lot faster, right? Now, the cool thing here is the code in this euler.zxn is not actually very special. Let me pull that up for you and I'll show you. Because it is itself written in the language that you're looking at, right? So here's the code, for example, for draw line. And zoom into that a little bit. Right? So here's the code for draw line. I never cheated and went and wrote it in assembler to make it look really fast. This is the actual code written in ZXN, and when we compile test.zxn, it pulls that file in and compiles all the code in this file, and then when we call the function, this is the function that runs. Same for the circle. Here's our circle function. Now the Euler plot function, that is a native function to the language, right? So it is written in assembler, a very short assembler function. I can bring that up and show it to you as well. You can find that quickly. Got a few Euler routines in here. So this is the assembly library that gets pulled in, and I'm using SJSM Plus modules, so it's Euler. and then you'll see the plot function, and it expects the D register to have the X and Y, and then uses the ZXN opcodes for calculating the screen address. So that's nice and efficient, right? Then used by the code here to actually set the pixels, but all of the logic for which pixels to set, etc. It's all written in ZXN. Right, so let's look at another example here. Here you see we have a little program. It's bouncing a bunch of letters around the screen. And looking at the code, so we're including another library, stdlib.zxn. Again, the library itself is mostly written in ZXN. Need to check there might be some embedded assembly as well. Right. One of the functions provided in that library is called set speed, which is what you saw me doing earlier when I was doing next reg to write to register 7 to set the speed. Effectively, that's what this routine does. Right. Similar to run at in ZXN Basic or ZX Spectrum Next Basic. Maybe you should consider changing the name of this function to run at as well. Then we're declaring a constant, right? Object count value 15. So it's the 15 letters you see running around on the screen there. Then we've got a struct called point, X and Y coordinate, with a move function or move member function that can be used to update the X and Y location based on the delta X and delta Y that's passed in. Then we've got a more elaborate struct representing a player. Right, the player's got a position, which is that struct that we declared earlier, and the direction that the player is moving in the X and Y coordinates, and the character representing that player. You can see if each one of these moving characters represents a player, they obviously all have a different character representing them. Right? And then there's an update member function as well that goes through the process of basically bouncing their character around the screen. Then we declare an array of player objects, right? Remember this constant was declared as 15 at the top. So we've got an array of 15 players, and we'll call that array P. And we loop through that array, so from 0 to less than object count, arrays in ZXN are 0 based. And we initialize some values for each of the characters. We set the position of the X and Y, we set the initial delta X to 1 and the delta Y to 1. And then we update the character. The first player is going to be letter A as a character, and each player subsequently will be the following character. Right? And then our main loop starts while true, so it's a forever loop, and we loop through each of the objects calling the update method. End result is what you see on the screen. Right? Now that's running at 3.5 megahertz. Obviously we can bump that up. Let's see what this looks like. Switch back to the code, we'll stop that execution and relaunch the program. And you can see it goes a lot faster. Right, so hopefully that gives you a little taste of the language. It's got support for sprites. I've got libraries for sound in, it's just very basic stuff, but probably enough to write some simple games that you might have seen in the 80s. Hopefully at some point I'll get around to doing that. That's really what has sort of been driving me to build the rest of this language out. Just thought, well, maybe I could actually build a little game using the language. And in the meantime, I've learned a lot about Z80, just trying to compile for it. So hope that was useful. If you found that interesting, let me know in the comments, and I'll happily make some additional videos about this. I was thinking about creating a video showing you how I actually add a new feature to the language. Today I have for loops and while loops, and one of the loops that constructs that I thought might be worth adding would be a repeat until, right? Where you're always going to run through the loop at least once, and will continue looping until a condition is met. Similar to what you'd have in C or C++, a do while loop, just obviously it's inverted from to until. Instead of doing it while the condition is true, it does it until the condition is true. So if you'd like to see how that goes, let me know, and I'll happily do that. Anyway, thanks for listening, and speak to you soon.